Section 5.3, Independence and the Multiplication Rule. We will look at these three objectives in this section. Objective 1, we want to identify independent events. Two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of event E in a probability experiment affects the probability of event F. So in this example, we want to identify whether or not these events are independent or not. For A, suppose you draw a card from a standard 52-card deck of cards and then roll a die. The events draw a heart and roll an even number are independent because the results of choosing a card do not impact the results of the die toss. For part B, suppose two 40-year-old women who live in the United States are randomly selected. The events that woman 1 survives the year and woman 2 survives the year are independent. They are independent because they were randomly selected. So this means that what happens with one of the women has nothing to do with what happens to the other. So when randomly selecting our individuals, it's reasonable to conclude that they're not related in any way. But now let's look at C. Suppose our two 40-year-old women live in the same apartment complex. Now they are linked by something common. So that causes our two events, that woman 1 survives the year and woman 2 survives the year, to now be dependent, because now that one woman survived the year might affect the likelihood that the other one did. Objective 2, use the multiplication rule for independent events. The multiplication rule for independent events states that if E and F are independent events, then the probability of E and F occurring is equal to the probability of E multiplied by the probability of F. In this example, we want to compute probabilities of independent events. The probability that a randomly selected female aged 60 years old will survive the year is 99.186% according to the National Vital Statistics Report. What is the probability that two randomly selected 60-year-old females will survive the year? Remember that since they are randomly selected, the survival of the first female is then independent of the survival of the second female. So we also have that the probability they will survive is equal to 0.99186. So then we can see, since they're independent, the probability the first survives and the second survives is equal to the probability the first one will survive times the probability the second one will survive. So it'll be equal to 0.99186 times 0.99186 again. Or we could write 0.99186 to the second power, since we're multiplying it by itself twice. And this would then give us a value of 0.9838. In this example, a manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it is purchased. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? So first we assume that the defectiveness of the equipment is independent of the use of the equipment. So then we have that the probability that it's defective and used will be the multiplication of the probability that it's defective by the probability that it's used. So the probability it's defective is 10%, or 0.10. And we'll multiply that then by the probability that it's used, which is 30%, or 0.30. And we'll get a value of 0.03. So now let's look at the multiplication rule for n independent events. If E1 through En are independent events, then the probability of E1 and E2 and E3 up to En is equal to each of those individual probabilities multiplied together. So to illustrate this, let's look again at our first example. Remembering that the probability that our randomly selected female aged 60 years old will survive the year is 99.186% according to the National Vital Statistics Report. So now let's look at the probability that 4 randomly selected 60-year-old females will survive the year. The probability that all 4 survive is equal to the probability the first survives, and the second, and the third, and the fourth. So we can take each of those individual probabilities and multiply them together. So we would write 0.99186 out 4 times and perform that multiplication. Or remember that we could simply write it once and raise it to the 4th power in our calculator. To do that, we type in our probability value, 0.99186. And to raise it to a power, we use the button right above the division sign. And then we hit the 4 for the power we want to raise it to and hit enter. And so then when we round, we see that we get approximately 0.9678. Objective 3. Compute at least probabilities. In this example, we want to compute at least probabilities. So we're looking back at our example still with our female age 60 years old. And this time we want to look at the probability that at least one of 500 randomly selected 60-year-old females will die during the course of the year. So the probability that at least one dies, that will be equal to 1 minus the probability that none will die. Remember that this utilizes our complement rule from the last section. So another way of saying that none will die would be to say that all of them survive. So 1 minus the probability that all survive is the same thing as saying 1 minus the probability that none of them die. So we're doing 1 minus the probability that all survive. And remember that that probability that one survived was 0.99186. And for all of them to survive, we have 500 of them. So we will raise that value to the 500th power. So we can put this in our calculator, and we have 1 minus 0.99186, and we'll raise that value to the 500th power and hit enter. And we see that we get 0.9832 as our probability that at least one will die during the course of the year. So let's look at the summary of all the rules of probability we've looked at. First, the probability of any event must be between 0 and 1. If we let E denote any event, then our probability of that event must be between 0 and 1 inclusive. 2, the sum of the probabilities of all outcomes in the sample space must equal 1. That is, if the sample space S is equal to our events E through N. then the sum of the probabilities of each of those individual events must be equal to 1. 3. If E and F are disjoint events, then the probability of E or F occurring is equal to the probability of E plus the probability of F. If E and F are not disjoint events, then the probability of E or F is equal to the probability of E plus the probability of F minus the overlap, the probability of E and F. And 4, if E represents any event and E raised to the C represents the complement of E, then the probability of E complement is 1 minus the probability of E. 5, if E and F are independent events, then the probability of E and F is the probability of E multiplied by the probability of F.